Good morning. Today's topic is sampling theorem and correlation with reference waves. In the last lecture, we have discussed about the evolution of productive relays, and we have seen that numerical relays have several advantages when compared to the conventional relays, and we have seen the development cycle of a new numerical relay. And then we have discussed about the flow diagram of numerical relay, and we have also discussed the components of numerical relays. We have seen that the important components are the instrument transformers, the anti-aliasing filters, the multiplexers, the sample input circuits, and the ADC converters. We have discussed about the functions of all these components in the last lecture. In today's lecture, we will see the sampling theorem. I hope that by the end of this lecture, we will be able to determine the minimum sampling frequency using sampling theorem. Moving ahead, I will start with the sampling theorem, the statement which we have already discussed in unit number 1. So I'll have a quick review of that one. And then we'll have a quick review of the proof of sampling theorem. And then we will move on to the correlation with the reference wave, the different mechanisms which we generally adopt for processing of a signal. We will see the Fourier analysis and Walsh analysis, and the Wavelet analysis. A quick review of all these things which you have already gone through in your unit number 1. Moving ahead, the sampling theorem. It states that before I move on to sampling theorem, one thing I would like to remind you that is a numerical relay, which is a type of your digital relay. Whatever the power system which you do have, whatever the analog data which you are measuring from your power system, it is to be converted to a digital data. And for that, the conversion of analog data to digital data requires sampling. Right. So it is, let us suppose you do have a signal like this one, which can be directly represented as 100 sine 314t. Let us suppose you can represent it as a continuous signal. But whenever you are supposed to feed it to your computer, you can't give it directly like this. What you are supposed to do? You are supposed to pick up samples, convert it into digital thing. So like that you should sample it. So how you can feed it to your system? At time t is equal to 0.01, its value is 314. Its time 0.03, it is 318. At time 0.05, it is 356. Like this you are supposed to provide it. It can't take a waveform and analyze it. So you should convert this data into digital data. And once this 314 also, it is to be converted to digital format. Just like your 110112, like sorry, 1. So everything is to be converted to digital data and then is to be fed to the system. So conversion of digital data, analog to digital data, that is done by ADC converters. Now the question is, how to sample the data? What is the sampling frequency? That is decided by a sampling theorem. It states that in order to preserve the information contained in a signal of a frequency, let us suppose this is a signal frequency, it must be sampled at a frequency which is at least equal to or greater than twice the signal frequency. This is the condition. A sampling frequency fs must be greater than or equal to 2f supply. This is your sampling frequency. This is the condition of your Shannon's sampling theorem. This lower limit, as already said, right? The minimum must be 2f signal. This is given by your Nyquist limits. If the signal is sampled well below the Nyquist limit, then there can be a concept of what you call it as aliasing. So what do you mean by aliasing? Aliasing is the phenomenon of given signal being lost in the presence of digitalization or digitization, and it takes place particularly because of a lower frequency wave. So Normally what happens is, even when in a power systems, you don't get a perfect signal which has a particular frequency. Normally what happens is the signals will be like this. So it is not a single waveform, it is not of a single frequency. So normally what happens is, so these higher order things are generally considered to be harmonics. We have dealt in unit number 1 also. So normally any signal may not be this purely sinusoidal, it will be having so many number of harmonics in that one. So whatever the harmonics which you want to consider, sometimes I am supposed to consider the harmonics also, they are of greater magnitude. So in that case, what I should do, my sampling frequency must be such that it is greater than or equal to maximum available frequency, or the maximum allowable frequency which you want to have near signal data. So if I want to keep up to 5th harmonic, so what I should do, my sampling must be greater than or equal to twice of maximum frequency which you are allowing in signal. It is not the signal frequency. This is the mistake which I have done in unit number 1 also. Okay. So if I write it in omega form, this is the equation. This is the sampling theorem. So why? I will teach you now. So let us suppose this is the time domain signal. Okay. Now I want to sample this one. So this is your sampling. I want to sample at this regular intervals. So once I sample this at regular intervals, this is my sample signal magnitude with respect to time. Now if I want to mention it in frequency domain, now let us suppose this is with respect to time, this is with respect to frequency. This is the spectrum of the signal. Now these have different frequencies because they are at different time intervals, so they will be having different frequencies. So these are of different frequencies. Okay. Now just like you mentioned it that you are sampling it with respect to this particular time, this you are supposed to sample it with respect to these frequencies. So the output will be like this. Right. This is a frequency spectrum which you might have not done. You should have done it in DSP or signals and systems. But okay, I hope you can understand these things, right? So this is your spectrum of your sample signal with respect to frequency. So there must be sufficient space between these things, right? So let us suppose if this is omega s, this is 0, right? Okay. This is omega n, right? Now this is omega s minus omega n, this is omega s plus omega n. This is 0, 0 plus omega n, this is minus 1. This is 2 omega s, 2 omega s minus omega n, this is 2 omega s. For your understanding, I'll write it like this. So let us suppose this is 0, this is omega s, this is minus 2 omega s. So your signal is this one, right? Omega n minus omega n. Here also omega s plus omega n, omega s minus omega n, right? There must be sufficient space between these two, right? So which means that the minimum, even though if they collide, there is a worst case, let us take. Right. So which means that omega s must be equal to here 2 omega. This is the minimum case. Okay. So normally this must be greater than this particular value, right? So in that case, you will get omega s is greater than or equal to 2 omega. This is what your sampling theorem. If it fails, then automatically what happens is there will be an intersection of these things, which means that you will lose the data while you are digitizing it. Understand? So this is the proof of your sampling theorem that I have already explained. Okay. So I hope that now you are able to. So if you do have a signal, so if it consists of too many number of harmonics, you better filter it, or otherwise you should choose your sampling frequency based upon the frequency which you want to have in the signal, maximum frequency which you want to have in the signal. Okay. Now, moving ahead, once the data is digitized, now the question arises how you are going to process the data. So, whatever the waveform which you do have, you should be able to mathematically correlate it with some sort of reference waveform, right? See, normally what I do is nothing but I will correlate it with the a sinusoidal waveform or a cosine waveform, or sometimes you'll be using it to correlate it with some sort of square waveforms. It depends upon your choice. So for that one, you are supposed to use some sort of transformations, isn't it? There are different types of transformations which are available. If you do have a waveform, see, try to understand. If you have a waveform like this one, you need to write a mathematical equation for that one, right? So how to write a mathematical equation? You will be writing it either in form of sine or cosine terms, or you can be writing it in form of rectangular terms, or you can write it in some other things also. Okay, so different types of reference waveforms you can choose. One such concept is Fourier analysis, where, see, it is a special case of such transformations wherein the orthogonal reference waves are sine and cosine waves. So what are the waveform which you do have? Mathematically, it is expressed as a function of your sine and cosine terms of different frequencies. If you don't want to use sine and cosine waves, then there is another option which you can have square waves with amplitude of unity of different frequencies. That is called as a Walsh analysis. Both of them we have discussed in unit number 2. Right. Let us suppose if the analysis is done with respect to scale and position of the reference wave, then the analysis is called as a wavelet analysis. Most of you might be doing your final year projects also. So the analysis is done with respect to scale and position of the reference. And in this wavelet analysis, there are so many mechanisms. One such one is Haar analysis. Okay. So whatever may be the analysis which you want to choose, one thing is very clear. You should be able to expand your function in different sets of orthogonal, in different orthogonal set of functions. Then only you can process the signal very easily. Now, we will see what is the difference between these different analyses. The first thing is a Fourier analysis. The Fourier analysis is basically what you will be doing is nothing but you will be correlating your waveform. You will be representing your current or voltage waveform in terms of some sinusoidal and cosine terms. So it is just like a finite duration continuous signals. It is analysis of that one, and it is normally known as Fourier transform. And if you do it in digital domain, it is called as a discrete Fourier transform. Okay. Normally, your numerical relays, they work with the digitized version of your analog signal. Therefore, for analysis described for Fourier signals, they are supposed to be suitably monotones. So this is the major difference between the analog and discrete domain. In analog domain, you will be having in terms of time, whereas in discrete domain, as I already told you, they will be discretized. So you will be representing the signals in sets of samples, sample 0, sample 1, sample 2. We have seen in unit number 2, right? In analog domain, you are supposed to whatever the signal which you do have, sine 314t, you will be integrating it to get your average value. But here, what you will be doing, you will be having the data will be like this: sample number and data 0, 1, 2, 3. What is the value of this one? So you are supposed to go with the sigma terms most of the times. Okay, and here you are supposed to represent it with respect to some frequency. Time period will be there. But whereas in this case, you will be representing it with number of how many samples you are going for one particular cycle. Okay. So this is a major difference between the processing in analog and digital domains. Now, most of the computer programs and relay software, they generally employ Fourier analysis itself. So the conventional Fourier analysis, it gives information about the frequencies that are present in the signal. However, there is a problem with the Fourier analysis. All clues about the time which these frequencies appear, because it says that the signal is having so many number of frequencies, but at which instant your frequency is appearing, that it is unable to say. That is the biggest problem with the Fourier analysis. So whenever you perform Fourier analysis, you can resolve your waveform into different sine and cosine terms, but which waveform is appearing at which time, that information is completely not available. So your Fourier analysis will not preserve that information. But regarding frequency, which frequency components are present, that data you can get it. On the other hand, digital or discrete Fourier transform is also there. It preserves some information regarding time, because whenever you are performing it with discrete Fourier transform, you might be knowing that which sample you are taken. So If you know that which time you are taking that sample, then you can get at least some small information regarding which frequency you are taking, right? But there is a problem again. The number of samples and the window size is most of the times it is fixed. You can perform only for a set of signals, year or length. In order to have more precise information, what you are supposed to do, your time window needs to be very smaller, and that is not possible. If you minimize the time window, then automatically what happens is nothing but the information about low frequencies will be lost. Okay. So in that case, your Fourier analysis may be a little bit tougher. So then came into picture this Walsh transforms. Walsh transforms initially they gained very popularity because in 1970s when microprocessors came into picture, they were not able to perform this floating point arithmetic. There was a problem. They were doing only problem with integers. So here sinusoidal and cosinusoidal terms generally they will be having so many floating point arithmetic, right? And that data was difficult to perform with your processes. So Walsh transforms came into picture. You might have seen in Walsh transform, we have done it in Walsh transforms. There will be only -1 or +1. There are no other components also present. So Walsh transforms gained importance in 1970s, but it had its own limitations. It is not true because we have been used to representing our electrical signals in sine and cosine. So converting them or having a reference of square waves was a little bit unconventional. And the modern microprocessors which came into picture, see the limitations. The modern microprocessors and digital microprocessors, they can routinely perform this data now. Now we do have high-speed microprocessors which can perform on floating point, and also in future we may get some processors which can work on complex things also. So the DSP process which we are employing, 63100, etc., they are capable of performing on floating point arithmetic also. So Walsh transforms are completely now. They are not used properly. Because once again we are getting back to our Fourier series. Because our electrical concept itself is deeply rooted in, so that's why I have mentioned, the electrical circuit theory is deeply rooted in sine waves. So this impedance concept, if you want to analyze it, the better thing is nothing but we should go with Fourier analysis. And with the advanced processes now, it has become easier for us. Okay, so if you want still to use Walsh transforms, again we need to convert it into Fourier transforms, and again we are supposed to analyze it. So it is a computationally intensive task. So that's why we are not employing Walsh transforms nowadays. And next came your wavelet analysis. Wavelet analysis, because as I already told you in Fourier analysis, we don't keep the data of time, at which time your frequency components are appearing. So that problem was eliminated with the continuous wavelet analysis. It gave information about which frequency component appeared at which time. So in wavelet analysis, I am also not familiar with the wavelet analysis. Just I have heard about this, and I have seen some kids doing projects on wavelet analysis. So very little knowledge I know about wavelet analysis, but I came to know that it was achieved by some sort of family of correlating functions which have well marked attributes of position and scale. Okay, this position attribute and scale attributes. Position attribute was used to correlate to your time instant of Fourier analysis, whereas scale it was representing a frequency domain. And the discrete implementation of this wavelet analysis was done by discrete wavelet analysis also. There was a concept of discrete wavelet analysis also. So on the whole, wavelet analysis is very useful. It was found to be very useful for analyzing signals. For stationary signals, stationary phenomena, Fourier analysis was widely used, whereas for non-stationary things, wavelet analysis was widely used. And in particular, when the system was in steady state, then you can go with what we call it as in steady state. We can go with Fourier analysis to analyze the system. But whereas when the system was experiencing faults, you might be studying about 3 different states: pre-fault, post-fault, during fault. Pre-fault, post-fault, system will be stable. So you can go with Fourier analysis. During the fault scenarios, during the transient things, where there will be non-stationary signals, there will be transients, the currents and voltages will be widely varying. At that time, wavelet analysis will be helpful for you a lot. Okay. So many approaches have been implemented in wavelet analysis nowadays. So Wavelet analysis is highly employed in transient analysis, particularly in fault analysis, whereas Fourier analysis is generally implemented in steady state analysis. Okay, so this is regarding your different types of analysis. A quick review. Now, which one you want to choose? It's your choice. How to analyze a signal. Okay, so my conclusion is regarding the sampling theorem. You must select samples. The sampling frequency must be selected such that it is greater than or equal to twice of the maximum allowable frequency in the signal. Okay, I hope that now you are able to state sampling theorem and what is significance of that one, what is anti-aliasing, and I hope that you are able to determine the minimum sampling frequency at which your samples must be collected. Okay, that's it. So these are the lecture practice questions. Practice them and we will discuss in class. Thank you.